All right, so we are pretty much done with propositional logic at this point. So what we are going to do now is to move on to the next major section, which is discrete probability. Discrete probability is the calculation of the probability of discrete events. And what I mean by discrete event is there's only so many numbers of possibilities. So this is not the same as what you normally learn in statistics, which is more general and applies to a non-discrete population. So let's go ahead and start with an example. The example that I normally like to start with is lotto. In other words, we want to calculate the chances that we win the lotto, we hit the jackpot in a with a lotto ticket. So the best way to learn that is to go to the super, what is it again? Oh, I cannot even remember the name of the lotto game. So let's find out lotto Powerball. That's it. Okay, there we go. All right, so this is the Powerball, which is a kind of interesting example of you know the calculation of chances. Obviously, this is only one of the applications, but turns out to be a pretty useful application of discrete probability. So the first thing we want to do is to learn the rule of the game. So we'll go to how to play. So right off the bat, there are some hidden information or implications that we kind of have to that I have to clarify. So the first thing is using a lottery payslip, which you can find in any lottery retailer. Pick five numbers between 1 and 69. So that's the range of these five numbers, and one power number between 1 and 26. So right off the bat, there are some implications. So the question is when we try to pick a number, or five numbers in this case, between 1 and 69, there are two main questions. One is, can I repeat the same number? In other words, can I pick a lotto ticket that is 1, 1, 1, 1, 1 for these five numbers? And the answer is no. So these five have to be unique numbers. Then the second question is if they are the unique numbers, then the question is ordering important? In other words, if I choose the five numbers, 1, 2, 3, 4, 5, is the ticket that lists 1, 2, 3, 4, 5 the same as the ticket that lists 5, 4, 3, 2, 1? The answer is they are the same. Okay, in other words, we only want to know whether a number is within the five number or not, but the position of that number is not important. The additional power number is only that because there's only one of them, so it doesn't really matter. There's no such thing as does it have to be unique because there's only one, and two, there's no such thing as ordering because once again, there's only one. So when you read the rest of the paragraph, okay, so it shows you can also select quick pick or just ask the cashier for a Powerball quick pick, and the random number generator will choose the numbers for you. So that means you basically do not buy. You can hand pick your numbers if you want. For instance, after you have read the numbers on a fortune cookie. All right, and to play the same numbers for consecutive draws, just mark advanced play. Advanced play allows you to play multiple draws with one single purchase. So basically, you just pay more money and you're sticking with the same number, but for multiple draws. You can play up to 10 consecutive draws in one pay slip by marking the advanced play box. Okay, so that part is more of a, how do you pay for your ticket more so than, the game itself. Step two, $2 per play for each Powerball ticket. Your ticket is your receipt, blah, 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 and so on. Know the draw time or the draw times. So when the draw time is basically, on which day and at which time the Powerball will be drawn, and you can actually watch it in real time. So in this case, Powerball draw takes place on Monday, Wednesdays, and Saturdays at 5:59 p.m. Draw entry closes at 7 p.m. on the day of the draw. So that means um, they only consider the tickets sold by 7 p.m. on that day, and then maybe about an hour later, they would perform the draw. All right. So now the question is, what about the chances of winning the jackpot? Okay, so you can go to game odds. It would actually tell you the chances. So in this case, to win the jackpot, what we call the jackpot is basically having all five numbers matching, and the Powerball is also matching. And the odds is 1 in 292,201,338. So this number is actually accurate, but the question is, how did they come up with this number? All right, so that means now we need to kind of take a look at the math behind all of this. So one way to show you the math is to kind of use a spreadsheet. And spreadsheets are really kind of helpful in many cases. So we're just going to use a spreadsheet in this case, and it's already in a shared folder. I'm going to use the date of the class, um, which is the 20, let me check my calendar here, 23rd. So it is 26/03/23. All right. So there, when you pick the first number, there are 69 of them. Okay. So you choose 69. And then the second number you have to choose that you can choose is going to be 68 because whatever the first number you have chosen, you cannot use it as the second number or the third number or the fourth number or the fifth number. So it's going to be this number minus one. And then this also applies to the third number. So the third number cannot be overlapping with the first or the second. So you only have 67 choices left. And then the fourth number, there will be 66 choices. And then the last number, you only have 65 choices. However, if you calculate it this way, okay, so let me just do a multiplication to show you, how many possible permutations we are talking about here. So I have to be careful to choose between the word permutation versus the word combination. Permutation is a case where 1, 2, 3, 4, 5 is counted as one possible event or one possible outcome, and then 5, 4, 3, 2, 1 is counted as a separate and unique possible outcome. But in this case, 1, 2, 3, 4, 5, 5, 4, 3, 2, 1, 1, 2, 3, 5, 4, 1, 3, 2, 4, 5, they are all considered to be the same. So we're going to have to handle, um, how do we deal with, uh, you know, counting the same um, how should I put it? How should we combine permutations into combinations? Combination is when ordering is not important. So 1, 2, 3, 4, 5, 5, 4, 3, 2, 1, they're all considered to be the same ticket. All right, but let's not worry too much about that. Okay, so we're going to multiply these five numbers. Okay, so that will give us a pretty huge number that is much larger than what we saw earlier. And then we also have to multiply this with the number of Powerball numbers. And let me go back and check, what that number turns out to be. We have to go back to how to play. There are 26. Okay, so let's go back to the spreadsheet again. And so there are 26 of those. So once we have this number, we have to multiply this number, which is the number of ways to choose five numbers where ordering is important out of 69. So we multiply this by 26. So this number is gigantic. Okay, this is not even in hundreds of million. So now the question is, how do we combine all the permutations of the same five numbers into one single combination. Let me say that one more time. You might want to slow down or pause the video, when you're listening to this. So let me restate what I want to do. I want to combine all the permutations of the same five numbers into one single combination. So that means I'm looking at 1, 2, 3, 4, 5. I'm looking at 1, 2, 3, 5, 4. I'm looking at 1, 2, 5, 3, 4, 1, 2, 5, 4, 3, and so on. And combining all of these, okay, where ordering is important, but it's the same five numbers being reordered. I want to combine all of these into one single combination. So if you think about this a little bit, we already know how to deal with that, okay? Because if I give you just five numbers, okay, let's just say it's 1, 2, 3, 4, 5, and I'm asking you how many ways can you reorder the same five numbers? The way we calculate that is actually pretty simple. It's actually something that we have seen already. Because if those five numbers are already fixed, the first place, okay, the first number that you can choose, there are five ways you can choose the first number. Okay, so we got five. Okay, there we look at my keyboard. So you can have five of those. Oh, actually, I don't intend to do it over here. So excuse me, I need to move on to the next row. So that means the first number, there are five choices for you. The second number is going to be four choices because whatever you choose to be the first place cannot be in the second, third, fourth, or fifth place. So now you can also apply the same thing over here. So that means when we look at the product of these numbers, okay, so we look at 5 times 4 and times 3. Oops, not this one. 3 times 2 and then times 1. That should turn out to be 120. Yep, there we go. So what this 120 means is there are 120 ways to order the same five numbers. But because the same five numbers is considered to be the same ticket, so we are basically saying, oh, okay, so there are 120 of these huge, gigantic number of permutations that are really belonging to be the same thing. So what we'll do now is we're going to do a division. So we are going to take this number and then we divide it by this number. And that is not the number that I was looking for. So I made a mistake somewhere, which is fine. Okay, so we will take a look at these numbers again. So we have, oh, okay, I see why. Because I forgot to multiply this by 26. The 26, I thought I did that earlier, but I guess I did not. So the 26 is corresponding to the Powerball number. So now, this number is exactly what we saw earlier. This is essentially this is the number of unique Powerball Lotto tickets that can exist, um, in the Lotto game. All right. So this is kind of cool, right? It gives us a way to calculate the chances of winning the jackpot in a Powerball Lotto game. Now we are going to take a look at some other things related to the Lotto game later on, because to win something, you can actually have a partial match. So if you look at the matches here, if you only match five of the five numbers, but not the Powerball number, this is the amount of money that you win, which is still kind of lots of money, $11,000,000 $688,054. If you match any four of the five numbers and also the Powerball number, you win $913,130 and so on. So that means you can so this is the overall odds of winning, which basically means if you buy lotto tickets 25 times, you're going to win something, okay? But most of the time, you're going to win none of the five, only the Powerball number. And the chances of that is 1 out of 39, so that's not too bad. The prize money that you win for each one of these matches is also listed here. All you have to do is to go to past winning number. I don't think this page actually show that. It does not. So if you go to the tab that we were looking at earlier, which is past winning numbers, this will actually tell you how much money you get out of each partial match. So the jackpot is last time. Okay, this is from March 21st. So it's $120 million is the jackpot, but nobody win it. So matching all five number is $1.2 million, and also nobody win it. There are three people who won four plus Powerball, so so they have 4 out of 5 matching with the five winning numbers, and then plus the Powerball number. So each one of those people got $12,000 ish. Okay, so when you go all the way down to just matching the Powerball number, those people get $4 back. So basically, it pay for the ticket that these people bought, and then plus $2 to buy the next ticket. All right, so that's basically how the game operates, with Lotto. So at some point we're gonna come back here and we'll try to figure out how many people actually bought the ticket. So before we do that, okay, I'm gonna give you another problem. It's called the birthday problem. So the birthday problem is kind of well documented, which makes it easy to look up and easy to learn. So we have the birthday probability problem or birthday problem. They basically work out the same way. So what we'll do is we're going to go to Wikipedia just to take a quick look at what the problem is. So the in probability theory, okay, which is in our case it is discrete probability. The birthday problem asks for the probability that, in a set of n randomly numbered chosen people, at least two will share the same birthday. The birthday paradox is the counterintuitive fact that only 23 people are needed for that probability to exceed 50%. Okay, so I'm not sure whether you understand what that means. Okay, so let me just kind of restate what the birthday problem is, and then we'll go work on how they come up with that answer. So let's just say that this is our class. Okay, and tax says, well, if at least two people are born on the same birthday of the year, okay, so the year does not matter. We are only counting the month and the day of month. If two people share the same birth date, okay, excluding the year, TAC is going to help throw a birthday party for for the class. Okay, so most people are going to say, well, that's not likely to happen because there are 365 days in a year. The class size is only about 20 something. So people would imagine that that probability is going to be less than 10%. So, but as it turns out, that is not the case. Okay, so we're going to take a look at how we can figure this out. So we're going to go back to the spreadsheet. Okay, I'm going to start a new tab here. All right. So what we are really looking at, okay, so the way we work on this problem is to not work on the direct problem. Instead, we're going to try to figure out what are the chances that everybody in the class, let's say the class has 20 people, what are the chances that everybody has a different birth date? Okay, because in that case, it means I don't have to buy, I don't have to host any birthday party because if everybody has a unique birth date, then it is guaranteed that no two people in the class share the same birth date. Okay, so we're going to work on this one first, and then what we'll do is we'll kind of subtract that probability from one, so that becomes at least two people sharing the same birth date, in a year. All right. So um, instead of working on 20 people, which means I'm gonna have to make the spreadsheet kind of big. Well, let's see. I suppose we can do that. Okay, let's go ahead and do that. So the first one, the first person of the class, in order for everybody to have a unique birth date, the first person can choose any day of the whole year. So that means that the first person actually can choose 365 days of the year. The second person can only choose, 364 days because whatever the first person has chosen, the second person cannot choose. So in this case, it's pretty much the same logic that we have kind of looked at before. So that means I'm just going to use this way to go all the way down to let's say 365 minus 2 plus 1. So that would make it 346. Okay, so we're gonna use a spreadsheet tool to do this, and we are getting there. Okay, so this is why I did not want to work with like 20 people because it's just kind of tedious. But at the same time, I'm gonna be able to show you some tricks in using spreadsheets, so that's kind of cool. All right, so column Y, all the way to column A. Okay, so I'm gonna decrease the column width a little bit just so that we can see everything, right? So now we want to multiply all of these numbers. Okay, for now we are going to do it the clumsy way. Okay, so to do this the clumsy way, let me see. This does not make sense. Right, it doesn't make sense because I should stop at column T. So all of these are not. Uh, they should not be factored in. So let me increase the column width a little bit back. There we go. Okay, so if you count, we should have 20 entries here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that is correct. Now we have 20 people. So when you multiply all of these, okay, the clumsy way is to do it the same way that I have done it before. But the other way to do this is to use a function that is called subtotal. So you would think subtotal does not make sense, right? Total is just adding. We need multiplication. We need the product. So let's go ahead and look up Google Sheets. Okay, this actually exists for Excel as well, um, but it's a really useful formula in any spreadsheet. It's called subtotal. So you can see, you can choose a function. So the function can be, it's not a total. Okay, so the name of the formula is a total misnomer. Okay, the name does not actually describe what it does. So if you go down here, you can now say, oh, okay, that's product, which is 6. Okay, so that means I can now go back here, okay, and I can say subtotal, subtotal 6 is the product, and we are going to choose A1 all the way to T1. Oops, I cannot type T1. There we go. Okay, so that should be a fairly large number. Okay, it is a large number. Okay, there we go. All right, so this number here, which is kind of huge, okay, this is the number of ways for 20 people to choose 20 unique dates out of 365 days. Okay, this is the total number of permutations in this case. So you would think, oh man, this number is huge. So now we want to figure out the probability of this actually happening. Okay, in other words, this number here, okay, the one that is selected right here, that is not a probability. Okay, this is it's a counter. Okay, it tells us the number of ways to choose 20 unique days out of a whole year. Okay, that's what this number is for. So what we need to do is to compare this to the actual number of ways if there's no restriction. In other words, in that case, everybody can choose any one of the 365 days. So that would be boring, right? Because everybody can choose any one day of the 365 because there's no restriction. But we still want to calculate, the number of ways for that to happen. And you can see that, oh, that is the total number of ways for the whole class, 20 people, and everybody can choose any day of the year. In other words, the people who are down here, okay, they don't have to say, oh, I cannot choose any day that these people have already chosen. Nope, this is like free form. So the probability that out of 20 people, and they all turn out to choose a unique date, is going to be the ratio of this number divided by this number. Okay, so let me explain these two numbers again. This number is representing the ways that 20 people can choose birth dates out of a whole year, but with the restriction that no two people can choose the same day. So that means, once a date is chosen by a person, all the people following that person cannot choose that date anymore. So this is this is the number of ways for that to happen. This number, on the other hand, is to say, well, I'm not going to put any restrictions. Okay, anyone can choose any day of the year, and that's why we have 365 across the all 20 people. So when we look at the ratio, okay, which is this number divided by this number, that's a probability. So the probability that everybody is choosing a unique birth dates out of 20 people is about 59%. So when we want to look at the probability of at least two people sharing the same birth date, which is exactly the opposite of this one, that means we are looking at, oops, 1 minus this probability, which is exceeding 40%. So that means even with a class, okay, with only 20 people in it, the probability that there are two people in the class, sharing the same birth date, okay, without a year, is already a little more than 41%. So that's actually pretty high if you think about it, because 41% is much higher compared to what people would think, because 20 people, 365 days, people would think, oh, it's going to be less than 10%. Oh no, it is quite a bit more than that. So the question now, okay, is how do we generalize this, right? Because working out the numbers this way using a spreadsheet is kind of cool, okay? It shows you all the calculations, but it doesn't really, it's not very scalable, okay? In other words, if I have a class of, let's say, 50 people, okay, what are the chances that at least two people of that large class are going to share the same birth date? Well, doing it this way is going to be the clumsy way. It's kind of hard to do. So what we'll do is we're going to introduce two functions here. Okay, in a spreadsheet, this number is known as permutation. Okay, because your permutation once again is choosing unique things. Okay, where ordering is important. So if someone is asking why is the ordering important, that's because it makes a difference whether the first person in the class, okay, let's say everything is sorted by student ID, whether the first person of that list is getting, let's say, April 1st, okay, um, versus the second person choosing, let me picking Pi Day, okay, so April 1st Pi Day, okay? That's one way for these two people to choose their birth date. But the reverse is a unique case. In other words, if the first person is born on Pi Day, which is March 14th, and the second person is born on April 1st, that is a different permutation because both of these situations can happen and each one is a unique situation. So that's why we are counting permutations, and that's why we don't have to divide 20 factorial, which is the number of ways for 20 numbers to be rearranged. Okay, so that's why this number is actually what we want. There is a built-in function in most spreadsheets to do this. It's called permut, okay, which is permutation. So to use that function, so what you do is you type an equal here, and then you say permut, okay, which is permutation, and then you have to tell the spreadsheet or the formula how many people to start with, um, or how many choices to start with. So in this case, we have 365 possible choices to choose from, and we want to pick 20 out of 365. And you can see that it is exactly the same number here. This number, on the other hand, is not a permutation. This is simply 365 times 365 times 365, 20 times. Okay, so that means we're looking at power. So this one is just using the power function, and the base is 365, and we are raising it to the power of 20, and that's why we see exactly the same number here. So that means now we can generalize, right? Because so let me start a new sheet here. We can now generalize. So on one column, we can say class size, okay, or the number of people. Well, we'll just kind of make it more abstract. We just call it n, okay, and we'll start with one, okay. We can actually start with zero, but we're gonna start with one. And then what we'll do here is we are gonna say the probability of unique birth dates of the whole class. In other words, there's no sharing of birth date. And then this one is going to be at least two uh, common birth date. Okay, so the both columns are going to be probabilities. All right. So now we have to come up with a way to do this calculation, but we already kind of came up with what we need to do. So with this one, we are looking at the permutation of 365, choosing this number here, okay? Because that's the number of people. So out of 365, that's the number of dates that we are choosing out of, okay? But then we have to divide it by 365 raised to the same power of exactly the same number. So in this case, it is going to be 1, okay? Because with only one person, the birth that out of that whole class of one person having unique birth date, that's a probability of one. That makes sense, right? So this number here, which is exactly the inverse, okay, the total, the probability of at least two people sharing the same birth date is going to be one minus this probability here, which is a zero when the class size is only one, because when the class size is only one, you cannot possibly have two people sharing the same birth date, okay? Because the whole idea of having two people sharing the same birth date is you need to have at least two people. All right, so now we can do the easy one here. So this is going to be just two, and then this one here is going to be, so I can now, use this feature here because everything is relative to the previous row. Okay. And now we can just kind of scroll this all the way to 50. Okay. Woohoo, 50. So we are past that. Still passing it, still passing a little bit. All right. So 50 is probably this row here. There we go. Okay. One too many. Fine. All right. So let's get rid of this. Okay. So what we're looking at here is if I have a class of 50 people, the chances that two people of that class sharing the same birth date is actually a little bit more than 97%. Okay, that's actually a pretty high chance. Okay, it's almost certain. Okay, so that is corresponding to the Wikipedia curve that we saw. Okay, so just look at this. This is 50, 50, right? So when you look at this curve here, 50 is here, and you can see that the probability is really close to one already if you look at this curve here. Okay, so that means, or if you are not convinced, okay, so let's just say that you're not convinced. So what we'll do is we'll go back to the spreadsheet here, okay, and then we'll do uh, just a little bit more, okay. So basically, you can go all the way to 365 people because if you have 360, oh, I take it back. If you have 366 people, okay, the chances the two people have the same birth date is going to be one, okay, because when you have 366 people and you only have 365 days in a year, by pigeonhole principle, right? This is actually a good use of the pigeonhole principle. Is there's one day of the whole year that at least two people are going to share, okay, because that's how we can reapply the pigeonhole principle. All right, so what we'll do is we're not going to go all the way to 365. We'll just probably, well, let me think. uh okay, I messed up somewhere. Okay, so let's go ahead and, all right, that goes pretty close, right? Okay, I think it will show you the curve already. So I think that's enough. Okay, just 100. The way this works is we want to plot this number against this column here. So let me see if my spreadsheet skill is good enough to do this. Okay, so we're gonna have to scroll down and do a shift, control shift click. Yeah, there we go. Okay, so I still remember how to do this. Cool. And we can zoom back in, okay, because that makes it easier to read. So control zero, there we go. And then we'll do an insert chart, okay. And the specific chart, okay, it knows how to do the chart, right? So this is basically the same chart that we saw earlier in Wikipedia. So let me just go back to Wikipedia and show you that's exactly the same curve. So that's the birthday problem. It is also falling into discrete probability. So that's one of the things that we're going to look into. All right, let me look at the time here. Okay, so now we are doubling back to figuring out, okay, with the lotto ticket problem, what are the probabilities that uh, that I can get, let's say, 3 out of 5 numbers matching and not matching the Powerball number. Let me go back to that page so I can talk about it. There we go. So we are focusing on just this one here. Okay, so of the 5 winning number, I want to match 3 of those, and I don't want to match the Powerball number. And I want to figure out the probability of me buying a lotto ticket, and the lotto ticket is going to give me a prize money of $7. Okay, and from the last drawing, uh, just about 3,000 people got this particular prize. But if you think about it, that's not a whole lot of people. California is a pretty has a lot of people, and of the entire state, the number of people who play lotto should be a lot, right? And out of those people, only about 3,000 people, got this specific prize. And I can use this number to backward project the total number of people who actually bought a ticket for that particular drawing. So let's go ahead and try to figure this out, okay? So we need 5 numbers. Okay, so there we go. We go back here and we go back to sheet one. So the way we figure this out is basically, so this time, now we have to be a little bit more careful. Okay, so we're gonna have to look at number of ways. Okay, so number of ways to choose 3 of 5 winning numbers. Okay. So the most important part here is assume that we already know the result of the drawing. In other words, we know exactly which 5 numbers are the winning numbers, of which we only want to choose 3 of those. Okay. And in this case, ordering is also not important. So instead of using permutation and then dividing it by 3 times 2 times 1, there's a function to do exactly that. It is called combin or combination. So combin in this case, the first number or the first parameter would be out of how many things we're choosing from. So because we already know which 5 numbers are the winning numbers, so we're choosing out of 5, and we have 3 of those. Okay, so this means once we know which 5 numbers are the winning numbers, there are exactly there are exactly 10 ways to choose 3 of those 5 numbers. Okay. Um, if you're not convinced, okay, if you're not convinced, so let's just say that the 5 numbers are 1, 2, 3, 4, 5, of which I want to choose 3 of those. So obviously 1, 2, 3 is 1, right? 1, 2, 4 is 1, and then 1, 2, 5 is 1, because your ordering is not important in this case. So that means your 3, 2, 1 is already covered by 1, 2, 3. So now we can say 2, 3, 4, 2, 3, 5, okay? And then we have 3, 4, 5. Okay, I am missing something here. 1, 2, 3, 1, 2, 4, 1, 2, 5. Oh, okay, I know what my problem is. Okay, so we have 1, 3, 4, 1, 3, 4, 1, 3, 5, and then we have 1, 4, 5. There we go. Okay, now we are now we are cooking. Okay, so we have 2, 3, 4, and then we have 2, 3, 5, and then we have 2, 4, 5. And then finally we have 3, 4, 5. Okay, so I think that should cover all 10 cases. Let's do some counting here. This is the first one. 1, 2, 3, 4, 5, 6, 7, 8, 9, exactly 10. So these are the 10 ways. Once we know which 5 numbers are the winning numbers, there are 10 ways, okay, to choose 3 out of the 10. Okay, so I can now erase that. It's just for illustration. But what about the other 2 numbers, right? Because you have 5 numbers on the ticket. These 10 ways is only telling us, how to choose the 10, how to choose 3 of the 5 winning numbers. So now we also have to combine with the ways to choose the non-winning numbers, okay? So now we have to look at the number of ways to choose 2 out of the remaining. So there are 64 non-winning numbers. Non-winning numbers. Because once you have chosen 5 to be quote unquote the winning numbers, the remaining of the 69 numbers, okay, so 69 minus 5 is 64, right? So you have to choose 2 of the non-winning numbers because your ticket has a total of 5 numbers. So that number, okay, so using combin, Combin, this time we have 64, okay, and we are choosing 2 out of the 64. So there are 2016 ways, okay, to choose 2 out of the 64 non-winning numbers. So these 2 numbers now need to be multiplied because each ticket has 5 numbers. So now we look at the number of ways to choose 3 out of 5 winning numbers. Okay, winning. I cannot spell winning numbers, and 2 of 64 non-winning numbers. Okay, I am going to make this look a little bit nicer. Okay, so we'll go ahead and do some formatting here just to make things look nice. Okay, there we go. It is totally unnecessary, but I just thought might as well do it. Go to format, merge cells. There we go. And then we'll just kind of make this one wrap around. Okay, so go to format, and then we can go to wrapping and just ask it to wrap. There we go. Okay. So that has to be the product between these two. So when we multiply this number by this number, so that would be the total number of ways to choose 3 out of 5 winning numbers. But we're also forgetting something here because there are 26 Powerball numbers, and we don't want to match the one Powerball number out of the drawing. Okay, so we have to multiply this number by 25 to get a total number of tickets that can win this particular prize. Okay, so now, I'm just gonna copy and paste this one over here because I don't feel like typing the whole thing. And 25 uh, of the 26 um, non Powerball numbers. Okay, there we go. So now we have to take this number, okay, we have to take this number and then multiply that by 25, okay, because there are 25 ways to choose a non-winning, uh, no, a non-Powerball number. Okay, there are 26 possibility, 25 are non-winning Powerball numbers because there's only one that is the chosen Powerball number. So now the number is kind of big. Okay, it's 5,000, 504,000. Okay, exactly. Okay, that's kind of cool. So now the question is, what are the chances, right? What are the chances that I will win this particular prize? That would be this number divided by the total possible number of tickets, which is this number over here. So now we can go like, okay, so we'll copy and paste again, but this time it's not the number of ways anymore, it is the probability. Okay, so this is going to be the probability to choose that. Okay, so the probability is always a ratio. Okay, it's always going to be one or less than one, but greater than or equal to zero. So this time it's going to be this number divided by this number over here. Okay, so the probability is it's actually pretty low. Okay, I'm kind of surprised at how low that number is. So I have to kind of think about this a little bit. Okay. So when you look at this probability, you go like, well, but Tech, you can just go ahead and go to the Lotto website and check, the chances of winning. Okay, so we go to game odds over here. We're looking at, any 3 out of 5, but not matching the Powerball number, and it is what? It's 100. It's 1 out of 580. So it's not the number that we're looking at here. Okay, that's because this number is the reciprocal of the 1 in chance, okay? So when we take the reciprocal of this number, okay, it is close to 580, okay? So the reason why they publish this number instead of this number here, even though this number here is really just the reciprocal of this number here, is because most people cannot understand what it means to be 0.00172 and so on, okay? But they know the chance of 1 in 580 because the idea of 1 in 580 is pretty easy to understand. Okay, you have 580 things. You're throwing a dart. Okay, it has to land on one of the 580 things. That's the probability. Okay, which is actually pretty slim if you ask me. So okay, so now we know this probability. Now the question is, how many people actually bought lotto tickets? Or this is approximation. Okay, it's never exact. It's just an approximation. So now we switch back to past winning numbers, okay? And then we look at the number of people who actually won that number. In other words, this number is representing 1 in 580. So if you multiply this number by approximately 580, you will get basically the total number of people, or the total number of tickets sold. So that's one way to do it, okay? But the other way to do it is simply to divide this number by the number that we just calculated, or the probability itself. So now we just do paste this number here and divide it by the probability, okay? Or you can multiply by the one in chance, okay, which is basically the same thing. And it doesn't like it because the comma is not supposed to be there. Okay, there we go. So in the last round, okay, in the last drawing, this is an approximation. So approximately 1.7 million people bought tickets, which is not a whole lot. The reason why not many people bought tickets in this case has to do with the prize money. Okay, if you look at the jackpot, okay, so the jackpot right now is how much? Uh, mm, it should be advertised, somewhere pretty obvious, but I cannot find it. Well, that's the last one. So basically, all the extra money from the non-winning tickets add to the prize amount, okay, or a good portion of that adds to the prize amount. So that's why initially once um, somebody won the jackpot, the next round is going to suck big time because not a whole lot of people are going to play, so the prize money will have to slowly increase again. But as the prize money goes up, more people are going to play, so that means the next for the next round there'll be more prize money. Okay, so this is kind of a strange thing. Okay, it's based on psychology. So anyway, but when you look at this number, um, it is too low. Okay, in other words, even if you win the jackpot, you only get 120 million dollars. But when you compare that to the odds of winning the jackpot, which is close to 300 million, so that means it's not the odd is not worth it, because each ticket costs you $2 to begin with, right? So you're spending $2 to buy a lotto ticket to try to win the jackpot, which is 120 million. But the chances of you winning the jackpot is 1 in 300 million. Okay, so that means it doesn't there's no payoff. Okay, the payoff does not calculate in this case. So you might ask then, why did 1.7 million people bought tickets when it doesn't make sense? Statistically speaking, it does not make sense. It's simply because it is the habit of some people. Okay, they just every week or every month, they have a certain schedule. They just buy a ticket every so often. Okay, it's just part of the routine. Okay, some people pay money to buy coffee, right? Starbucks or whatnot. Okay. And some other people just decide, okay, I don't want to drink my coffee. Okay. I want to spend the $8 that other people spend on coffee, and I want to buy four lotto tickets. Okay. Which is fine. Okay. That's not a problem. But that's why, there are still people playing when the payoff is relatively low. All right, let me take a look at the time. Okay, it is about an hour, so I still got some time to go. I know, because without an actual class, I can actually end a lecture a little bit early. Okay, just because people do not have a chance to ask questions, and without that interaction, things are a little bit more condensed, and you know, I really if I use all 80 minutes, in a lecture recording without interaction, that actually covers a lot more content than being in a class, being interactive. Because when it's interactive, people would ask questions. I get, kind of sidetracked a little bit sometimes, and other times, I just, need time to answer the questions. So anyway, getting back to the question of, when is it worth it to buy a lotto ticket from the perspective of statistics. Okay, so let's try to figure that out. Okay, so that means when you look at this number and it costs you $2, okay, to buy each ticket. So we'll do some calculations here. So what we'll do, let's see, I'm going to use this column here. So $2 and this is the total number of tickets. So if you somehow can pony up $584 million, dollars, you can buy every single possible ticket there is to exist. Okay? So that means you're guaranteed to win the jackpot. Okay? Which the other way to look at this is without any taxation, okay? And the jackpot is let's say about $600 million, and you can somehow arrange your finance to buy every single possible ticket, then you're guaranteed to win the jackpot. Okay, so you're guaranteed to quote unquote break even when this is the jackpot money. Unfortunately, the government wants a cut of your money. Okay, when you win big, the government wins big too because it wants a cut. So now you have to look at the tax bracket, both federal and and state. So for that, I'm gonna ask AI. Okay, so what is the tax rate? Okay, combining federal and California state of an income of $600 million. Okay, $600 million. Okay, there we go. So let's see what uh, the AI has to come back with. Okay, so approximately 50%. All right. So that means you need a buffer, right? So you need twice this amount of money in order to pay all your taxes and just to break even. There we go. Okay. So you're gonna need 1.16 trill no let me take it. Yeah, $1.16 billion. Okay. So 1.16, well, let's call it 1.17. So you need $1.17 billion, okay, to buy all the tickets. Okay. Spend some money, okay, spend half of it to buy all the possible tickets, and then let me see. Oh, no, no, I take it back. I take it back. Okay. So you need to borrow this much money to buy all the possible tickets. And the payoff, has to be at least this much money. When you win the jackpot, because you have to, no, I take it back again. Okay, never mind. I take it back. Okay, let me say that one more time. You need the jackpot to be this money. You need the jackpot to be 1 point. Oh, I just messed up my sensor here. Okay, so you need the jackpot to be about $1.2 billion, and you have to borrow this much money to buy all the possible tickets. When you win this much money, you're gonna return this much money to the bank, and also pay this much money to the government, okay, both federal and your state tax, and then you have basically $0 left in your pocket. Okay, that is basically what is happening. Now, that is not entirely true. You will still end up with some cash in your pocket. The reason why you will still end up with some cash in your pocket is you are also going to win all the smaller prizes. In other words, you're going to win the all five, 5 out of 5, 4 out of 5 in the Powerball, 4 out of 4, and you're going to win all the possible tickets to win each one of the sub prizes. You're going to get it too. Okay, so that's going to be your actual uh, income, because, well, that's going to be taxed too, by the way. That's also going to be taxed. So, the number that I figure out here does not factor in the surprises that you can win. So you're gonna have to factor in all the surprises that you need to win, that you get to win, and also to factor in the taxation of those money. So that means the jackpot actually. Let me think. No, that's gonna be okay. Yeah, so the jackpot can be a little bit less than this money to quote unquote break even. because the sub prices, the smaller prices will still be part of your income, even though your loan money is only this much. So you still end up, kind of winning some money. You actually end up with some money in your pocket if this is the actual jackpot, because the smaller prices, I think some of the top few are based on the jackpot. The rest are constant, so that portion does not depend on the jackpot. So anyway, this is just a rough calculation of when it is actually worth it to buy a lotto ticket, right? Just from the statistical perspective. But there's one more thing, okay? Multiple people can buy the same. I shouldn't say the same. Multiple people can buy their lotto ticket, and they all win the jackpot at the same time. Because if you can think about this scheme here and go borrow $584 million, other people would come up with the same idea, right? So basically, you have to split the jackpot across all the people who also win the jackpot. So that means this number is going to be divided by the total number of people who win the jackpot. So that means that is a difficult part to model. Is how many people will win the jackpot. Um, you can actually go back to the history of Lotto. Okay, let me hear. There we go. So if you go back to past winning number, okay, so I cannot remember the last time when the jackpot was really high. I'm gonna pick this one here. Okay, that's not very high, um, but it's higher than what it is now. Okay, so it went up and then somebody won jackpot, I think. So 200. Okay, let me see. Okay, now we got reset back to 200 million. So it has to be before March 4th and after the previous date. So so this is 203 million, and it got all the way back down to 20 million. So the one right before has to be the one where one person hit the jackpot. No. Okay. Why did it reset to? Did I get the date wrong? No, I did not. Hmm. I don't get it. Why is the prize amount? Why did it drop from 249 million all the way back down to 20 million? Hmm. All right. Well, I am at a loss here because it doesn't seem to make sense. Um, did I miss something here? No, it keeps increasing and then it dropped all the way back to 20 million. I think the Powerball may be a national thing, and these winning tickets is state only. So that means someone from out of state might have won the actual jackpot. That's my guess. Okay, I'm not, since I don't buy lotto tickets. I don't know whether it's a national thing or whether it's a state thing. Anyway, I hope this lecture is giving you some idea of the application of discrete probability. Now, obviously, this is not a very good application of discrete probability. Okay, so it goes way beyond just for analyzing the chances of winning a particular prize in lotto or to calculate the birthday problem. There are actual practical applications of discrete probability. But this goes back to our notes here. Okay. So for Wednesday, I would like you to read a chapter or a module simply titled as counting. And if you can finish this one, then we would also it might be helpful to also read discrete probability. So counting is it's about nomenclature. Okay, it's about what word, okay, is defined in which way to describe what aspect of discrete probability. So that way we can basically build up the basic vocabulary in order to understand, to describe the problems that we need to solve. So it looks kind of boring, looks kind of dry, but it's actually really important to get all the terms understood. It also includes some kind of obscure stuff, okay? When we get to it, we'll see it, okay? And all the calculations, how is permutation actually expanded, okay, using factorial? How is combination using is expanded using permutation and factorial? So we'll answer all of those questions in this particular module. It is going to be quite helpful if you read it ahead of time, and that's going to be what we'll be talking about on Wednesday. All right, so I think that should be enough material, from a perspective of read only without interaction. And then on Wednesday, we'll go back to the full interaction mode. So if you have any questions about this particular lecture recording, bring those questions on Wednesday, and I'll try my best to answer those questions. All right, I'll see you on Wednesday.